Oh, hang on. Let me just check my audio settings here. Okay. All right. You guys can hear me okay, I think. All right. Well, we will get started. I appreciate your flexibility again in meeting at a slightly different time and meeting online instead of in person. I do like meeting in person, but yeah, just a couple personal things going on and have to be at home right now. Okay, let's take a look. Our lecture today is going to actually it says actually I need to change this. It's a important sampling. Important sampling is the title. I copied and pasted the heading, I guess, from the other lecture. It's correct here. This is the topic, important sampling. But that cover page was wrong. Okay. We left off on Monday and we said we can do this thing, Monte Carlo integration. Okay. And so in Monte Carlo integration, we are saying we want to get the expected value of some function applied to a random variable, right? So we have x is this random variable. The PDF of x is f. We're able to generate values from x. And if we want to get the expected value of this function applied to x, we could do it like this, right? So for example, a chi-squared distribution is a random normal variable, but you square it. And so, what is the expected value of a chi-squared distribution with 1 degree of freedom? You could go through the math, and I think you do it in 100B. You do it analytically to get the mean of a chi-squared distribution. What we would do, the Monte Carlo approach would just say, hey, let's just generate a whole bunch of values from the normal distribution. Let's square them, and then let's take the average. And that's got to be kind of close to the real answer. And that's basically what we do in Monte Carlo integration. We just generate a whole bunch of x values. We plug them into h of x, and then we take the average. And by having a whole bunch of x values generated, it kind of takes care of the idea that our x values get multiplied by f of x, just because the values that are more likely to appear where f of x is larger are going to appear more frequently in our random sample. Values where x is less likely to appear, where f of x is lower, the PDF is lower, those are going to appear less frequently. And so, when we generate a very large sample and we take the average, we're going to get something close to this expected value. All right. And so this is h bar sub n is our Monte Carlo estimator of this quantity, okay, or this integral here. All of this works because we're able to generate values from this random variable x. We're able to generate random values for x. If we're not able to generate values from random values from x, then the whole thing kind of falls apart, because what we need is when the PDF of x is high, we need to generate those values more frequently. When the PDF of x is low, those need to be generated less frequently and whatnot. So all of these things depend on our ability to generate random values of x accurately. And what we do right now is we're using R's built-in functions. So R has a whole bunch of functions built into it that allow us to generate random values, right? We have R norm, and that generates random normal values. We have R unif to generate random uniform values. And any other thing, you can do R gamma, you can do R beta, R exp for exponential, R chi-square, RF, a lot of these kind of classical probability distributions, you can generate random values from this thing, okay? But we might be in some situation where we don't have a built-in random distribution function. Or perhaps, we're in a situation where, we want to do something a little bit different. So what do we do in these kinds of situations where we don't, the random generating function either doesn't exist or is inadequate, right? If we're not able to sample directly from that PDF f of x, well, one thing we can do is we have techniques to generate random values from different distributions. And we'll take a look at that next week. So next week, we will look at some methods for generating random values from different distributions. And so we have like the inverse CDF method, and we have rejection sampling, and we have these different techniques. Okay. But what we're going to look at today is something called importance sampling. So importance sampling is a technique where we basically, it's a way for us to compensate not being able to generate from this distribution. Now, I don't really like the name importance sampling. Importance sampling sounds like it's a sampling technique. And next week, we will deal with sampling techniques. Sampling techniques being things that generate random samples of values. So, coming up with, a technique to generate random normal values or random values from some arbitrary distribution. Those are sampling things, and this name importance sampling sounds like it's a sampling technique, but it's not a sampling technique. It's really kind of like Monte Carlo integration, which we covered on Monday. It's really that, but we apply a weight to it. So if it were up to me, I would name this thing weighted Monte Carlo integration. But it's not up to me. It's the title is importance sampling, and if you wanted to learn about it on Wikipedia, you would type in importance sampling and whatnot. But yeah, in my opinion, it should have been named something else. But anyway, so again, this is what we want to do. The problem that brings about importance sampling as the solution is that we're not able to generate values from this distribution F. So X is the random variable, and its PDF is the function F. Okay, but we're not able to generate from this function F. So we're going to say, let's generate values from a different distribution, G of X. And that seems like, well, how's that going to work, right? We're going to just generate values from a different distribution. And it'll be okay, all right? The only, basically this different distribution G of X, the only requirement is that the support of F has to be fully contained within the support of G of X, okay? So, if you have, if F is defined, if F is some PDF, right? And it's defined like this, or I don't know, let's say you have a beta distribution going from, say, 0 to 1, okay? And F is inside here, then as long as G, as long as it's contained within G, then that's fine. And G could be something even bigger, right? Like you could have a normal distribution that goes from negative infinity to positive infinity or something. So it's just the support of F of X has to be within the support of G of X. That means for G of X is greater than 0 for anything that's for all values in the support of X. So you can't have any G of X equal to 0. It has to be strictly greater than 0. You can't have any G of X equal to 0 for any value in the support of F. And what we do, okay, so remember what we want is we want the expected value of the function h applied to the random variable x, where x comes from this distribution F. And we said, okay, well, that's equal to h of x multiplied by f of x. And then this is how we go about doing it. We say, all right, I'm going to multiply this by g of x divided by g of x, okay? And as long as g of x is greater than 0 for all values inside the support of x, we're never dividing by 0. So that's why I can do g of x over g of x here. Okay, and basically I just rearrange a couple things, and now, right? Now, so keep in mind this integral is a arbitrary function times PDF dx, right? That's what we have. H is an arbitrary function, f of x is a PDF. And this is what we're doing. We're saying this part, now we're basically saying let the arbitrary function equal h of x times f of x over g of x. Okay, let that be our arbitrary function. And then this part is the PDF, okay? And the PDF is equal to g of x. So basically this thing up here and this thing, they're in the same form. It's just here we went from the PDF is f of x, and now the PDF is equal to g of x, right? And so therefore, this is equal, this is going to be the expected value of now this big kind of crazy arbitrary function. It's h of x times f of x over g of x. It's just this big function now, but it's just a function where x is a random variable that comes from, that has PDF g of x, right? So here we have this is this. So we can say the thing that we're after, the expected value of h applied to random variable x, where x has PDF f, is equal to the expected value of h applied to random variable x multiplied by f of x divided by g of x, where x is a random variable that has a different PDF, a PDF g. And that's what we have here. Okay, so that's importance sampling. That's the math behind importance sampling. So what does this look like when you try to carry it out? Well, the idea here is we aren't going to sample from f of x. We need to be able to evaluate the PDF of f of x. So we do need to know what the PDF is, right? So I guess, so we are able to sample from g of x, okay? And I'll say, and we know, the PDF of g of x, okay? And here we also know the PDF, PDF f of x, okay? So we also know the PDF f of x. We can't generate samples, random values of x, but we can estimate this desired quantity. We just generate values from g of x, and then we compute our function h of x times f of x divided by g of x. We compute that for all of the different values of x that we generate. And then we take the average. And that's it. That's it. And it works. It works. Somehow, like, it feels like, I don't know if any of this feels like magic, but to me it feels like magic. As we're saying, I don't know how to get this sample, so here's a completely different sample. And even though I have a completely different sample, I'm still able to estimate this quantity that depends on a different random variable. Let me try doing some examples here. I wrote this slide on how does this even work, right? So we are generating values from a totally different distribution. We're generating values from a distribution g of x, okay? But what we want is we want to get the expected value of this function h of x as if the random values of x were coming from a different distribution, f of x, right? So we have some distribution f of x. We're generating values from a different distribution. On Monday we said, hey, if we can generate values from f of x, we just plug those into our function h, and then we take the average, and it works. But here we're going to say, well, I can't actually even generate values from f of x. We still want to plug in our values x into a function and get an average. And we're going to say, well, where are your values coming from? Well, they're going to come from g of x. G of x is something else entirely. Can we still estimate our quantity? And the answer is like, yeah, I guess so. We're going to generate values from g of x, and then we'll plug it. We'll modify them a little bit, and then we plug them into our function, or we plug it into our I guess a modified function, and we still get an estimate here. It's like cooking when you don't have the right ingredients. So it's like, okay, I want to make chicken tacos. And you say, well, I don't have any chicken. Okay, well, no problem. I've got beef over here. And you say, all right, well, here's this other kind of meat. And we're going to just kind of do a little bit of magic. And we're going to get something where it's going to feel a lot like, the thing that we want. Right? We're generating what we have is something totally different from what we want, and yet we still somehow make it work in the final answer here. So this is for a starting example, we're going to say the distribution that we desire is a beta 2,4 distribution. We're going to say this is what we want. Okay, but unfortunately, we can't generate from f. We are able to generate from g, which is a beta distribution with shape of parameters 5,3. Okay, so this is silly, because if my computer can generate from 5,3, it can probably also generate from 2,4, beta 2,4. But this is just to say, can we do this kind of solution? I don't know. It's kind of like, what if you placed an order for random values, and then after the fact you realize your order was wrong, right? You say, oh no, I ordered a bunch of values from this distribution, 5,3, but what I really wanted was the values from this distribution, beta 2,4. But now I've got, a million values from beta 5,3. Can I do anything with them? Do I just have to throw them away and get a brand new order or something? And importance sampling says, oh, no, you just weight your values appropriately, and you can get a pretty good estimate. Okay, so this is this distribution over here. This is f of x. This is the beta 2,4 distribution. All right, and then over here, this is beta 5,3, I believe. Yeah. All right, and this is g of x. So we are able, okay, we can generate values from g of x, but what we really want is we want our distribution to look kind of like the blue distribution. So, what do I do? Okay. If we look at the beta distribution, what is the mean of the beta distribution? The mean of the beta distribution is 2 divided by 6. The mean is 0.33. The mean of G, the red distribution, kind of the average here, if you were to average, is 6.25. So, here's 0.7. And if I divide this into 3 parts, this is the mean over here. And over here, this is what, 0.3. And this is 0.333. This would be the mean of F. And this over here is the mean of G. And we can see that, so I don't know, let's say I didn't know this mean, it was 0.33, and I wanted to get an estimate of what is the mean of F, right? The classical way is, if I could generate from the beta distribution 2, 4, I would generate values from the beta distribution 2, 4, and then I would take the average, right? And that's pretty easy. If you don't know how to calculate the mean of something, just generate a bunch of random values and then take the average. And that's going to give you a pretty good estimate. But here we're going to pretend we're in this situation where we can't generate values from F. Your computer, for whatever reason, is broken and can't generate values from this beta distribution. So we're going to say, well, what I am able to do is generate values from G. And we do. Okay, we're going to say I'm going to generate using R beta. I'm going to generate 100,000 values from R beta with shape parameters 5, 3. And if I say, hey, what is the mean of all of these values? So remember, all of these values are coming from the red distribution, and I get 100,000 of them, and I say, hey, what's the mean of my 100,000 values? And the mean here is 0.625, and that makes sense because the mean of the beta distribution is 0.625, right? So this is the mean of my beta distribution, and that's what I'm getting when I get, this is the sample. X is length 100,000, and the mean of X is very, very approximate to 0.625, and that's what we have right now. But can I take this sample of X to estimate this thing? Well, yeah, what we're going to do is we're going to multiply it by our importance weight. Our importance weight is basically the ratio between the PDF of F divided by the PDF of G. Okay, so if we look back at this, okay, basically the values I have are red, are coming from the red distribution. And we're, I'm gonna, like, if we look at the number, say 0.7, okay, values in the red distribution, I'm gonna have way too many values, right? Because here the red distribution generates with this probability, a very high probability, lots of values from 0.7, and in F of X, I only need a few of them. Okay, so what I do is all of those values, okay, all of those values that come near 0.7, they get weighted less, right? So when I draw a value from G that's close to 0.7, I'm going to draw a bunch of these values. I'm going to weight those values less. So compared to F, I have too many of them, so I reduce their weight. Okay. On the other hand, G of X does not produce very, very many values near 0.2. Okay. Whereas F of X does produce lots of values near 0.2. So when I do get a value near 0.2, all right, I have to make it count. I weight it a lot more. So I give it a weight if the ratio between F divided by G is going to be a number a lot greater than 1. Okay. And so here you can see why the support of F has to be fully contained in the support of G, because if it's not, then you're going to have places where F is not 0 and G is equal to 0, and then you're dividing by 0, and that's a problem, right? So wherever F is not 0, G also has to not be 0. If F is 0, then it's okay if G is 0, because these values will just never appear. But if F is non-zero, then G also has to be non-zero. And so, we weight all of these things. So it's kind of, if you wanted to get a random sample, or a representative sample of, say, UCLA students or something, okay? And I think the current gender split of UCLA undergraduate students is around 59% female, and 41% male, I think is the current gender split, something around there, okay? Give or take a few percentage points, and that's not including non-binary individuals. So something, approximately a 60-40 split, okay? But depending on, what major you look at, okay? So certain majors have, a lot more female students. Certain majors have a lot more male students. So, let's say you went to, for example, I think art history. Art history is a major that, for whatever reason, is much more popular among women and less popular among men. And so, you might have, say, let's just say 90%, okay? 90% women and 10% men if you take a random sample of art history students at UCLA. And if you wanted to get a, I don't know if you, this is not a random sample, but if you wanted to do some kind of survey and try to get an average of all of UCLA or something, if you used just your sample from art history, you would have, too many women and not enough men. And so, but if that was the only thing that was available to you, like you're only allowed to survey or interview people from the art history department, then what, you could compensate for this by kind of, anytime you encounter a male student, you have that, like this individual, is kind of like multiplied to be, weighted more importantly in the survey results. Okay, it's weird. It's a little awkward in terms of like you weight certain value responses more heavily and other responses less heavily. But that's kind of how you compensate for the fact that your sample is not necessarily representative of the kind of final population. And that's actually what a lot of, say, in public health surveys and stuff, they try to get representative samples from the United States or something, and as they select people to be part of their sample, it's hard to get something that's truly representative. So if they have too many or not enough, those values get kind of weighted differently. And that's basically what's happening here. All of the values that we generate randomly coming from G of X get a different weight, right? Depending on the ratio between f of X and G of X. Okay, let me give you your first view quiz answer. Our first view quiz answer is the letter D. Okay, so question 1 is D. So I'm going to use this same exact sample. So remember, my sample came from the wrong beta distribution. And I'm going to calculate the weights, the weight for every single X value. So I have 100,000 values in X. And I'm going to calculate, okay, what is the PDF, right? So remember, D beta is the PDF of the beta distribution, is the density. So I'm going to say, all right, what is the PDF of the beta distribution with shape parameters 2, 4? And I'm going to divide by the PDF of the beta distribution with shape parameters 5, 3. And so this gives me a vector of weights, basically length 100,000 for each value of X. And then we take each value of X and we multiply it by its weight. And then we get the mean, right? And here my estimated mean is 0.3328. 0.3328, which is pretty close to the true value of 0.333. Okay. And here my X values, again, came from the wrong distribution. The X values came from beta 5, 3. And if I plotted a histogram of my X values, so if I say, here's a histogram of X, we can see, yeah, that histogram does look like the beta 5, 3 distribution. So it lines up. And if I take the mean of x directly, I get 0.625. But if I do this little thing where I weight each of the values by the ratio between their two densities, their two PDFs, and if I weight them appropriately, I get 0.332, okay, which is close to the value that I want. So that's important sampling. I have I guess a couple more examples, but this is the key concept here for important sampling. We want to generate values from the blue distribution. We're not able to generate values from the blue distribution. So we generate something from a different distribution. In this case, it's the red distribution. But we want to be able to estimate quantities based off the blue distribution. Well, we just kind of plug our values into the function anyway, and then we just weight each of the values differently. We say these values appear too frequently, so we weight them less. These values in my sample don't appear often enough, so I need to weight them more heavily. And that's what we do, and we get an approximate answer. That's important sampling. Okay. All right. So this is what we have here. We can just say we can kind of revise our algorithm. We're going to say just generate a whole bunch of values from the distribution that you're able to generate from, g of x. And then rather than computing h of x times f of x divided by g of x, we're just going to calculate f of x divided by g of x for every single value. Okay, so we're going to calculate the weight for every single value that we draw, f of x divided by g of x, f of x divided by g of x. So, again, we need the PDFs, and g of x cannot be 0 if f of x is non-zero. Otherwise, we're dividing by 0 and it breaks everything. So your selection of g of x is important. You have to have a distribution where the support of g of x fully contains all the values in the support of f of x. And we're going to say the expected value of h of x applied to x, where x comes from a random, where x comes from a PDF f, is equivalent to the expected value of x of this function applied to x, h of x times f of x divided by g of x, where x is generated from this from a PDF with function g, and that can be approximated by taking all of our randomly sampled values x, plugging that into h of x, calculating the weight for each value, and then taking the average. Okay. Oh, sorry, there's a typo here. It should say j equals 1. J equals 10. Okay. All right. So let's just try another example, and I'll probably end up finishing a little bit early. Okay. Let's say we have something called the folded normal distribution. This is basically what do you get if you have a normal distribution and then you take the absolute value, right? So let's say you generate values from a normal distribution, but you take the absolute value of the normal distribution. What is the mean? What is the mean if you generate values from the normal distribution and you take the absolute value? Okay. Well, here, this is, again, a contrived scenario. Again, this is a little bit silly because we can generate values from the normal distribution and we can calculate absolute values. So if we wanted to do this, it'd be really easy to do it directly, but we're gonna just pretend we can't do this thing directly. All right, what is the PDF gonna look like? Okay, so if you think about the PDF of the normal distribution, it looks like this. Okay, and this total area equals 1. Okay, and now we're gonna have and now I have a normal distribution, but I've taken the absolute value. And so in order to kind of preserve that, the fact that it's a PDF, it's really hard to draw. My normal distribution has to look something kind of like this, right? Because again, the total area has to equal 1. It has to be twice as tall, because really I'm limiting myself just to the right-hand side of the normal PDF. So basically, I'm going to take the normal PDF. This is the standard normal PDF over here. And then I'm going to just multiply it by 2, right? Because the PDF is of the standard normal. We have to take it and I have to just double its height so that the total area, because I'm integrating only from 0 to infinity, in order for that to have an equal area equal to 1, this is going to be my PDF here. Okay, does that kind of make sense as far as the PDF of this folded normal? And here the support of X is going from 0 to infinity. Okay, we're not going to worry about the negative side here. What is the mean? What is the mean of this distribution? So what is the expected value of f of x, where x is coming from this PDF over here? Okay, so in this example, our h of x function is just x, okay? All right, and so we're going to use importance sampling in this scenario. Okay, so I could just cheat and get the answer directly. Because I could just say, hey, let's just generate 1,000,000 values from the normal distribution. Let me take the absolute value from the normal distribution. Let me calculate the mean. And our answer is 0.79738. Okay. That's the true approximate answer. Okay. But we're gonna pretend that we can't do this. All right. We're gonna say, all right, I'm not able to generate from the normal value. I don't know how to do this. So in our situation, we're gonna, rather than generating values from the normal PDF, we'll generate values from another distribution. We're gonna say, I'm gonna generate values from an exponential distribution. Exponential distribution with lambda equal to 2. All right, so the PDF of an exponential distribution is lambda times e times negative lambda x, okay? So lambda distribution, I'm sorry, exponential distribution with lambda equal to 2 is 2e to the negative 2x. That's the PDF there, okay? Exponential distribution basically just looks like this, right? And the total area here for all PDFs, total area is equal to 1. And that's basically what an exponential distribution looks like. And what is the support? The support of g of x here. So if this is my g of x, the support of g of x is basically x is in 0 to infinity. Okay. I guess square bracket 0 to positive infinity. Okay, and we can sample values from the exponential distribution using R exponential, REXP. Okay, so this is what I'm going to do. I'm going to generate a whole bunch of values from the exponential distribution with lambda equal to 2. And I'm going to compute the weights for every single one of these things, okay? This here, this is 2 times equal to 2 times the PDF of normal, right? And then this down here, this is the exponential PDF. And so on the computer, I can just do 2 times d norm, right? The PDF is d. So I'm going to say, all right, I'm going to just plug in whatever my value, random value is. I'm going to say, all right, what is 2 times d norm on that? And then I'm going to divide by the exponential PDF, which is d exponential. And I'm going to plug in, say rate is equal to 2. So I'm going to get weights for every single xj. And then, and I'm going to multiply that by x here. So I'm going to just basically do x times my weights, because my h of x in this case is just x. And we're going to calculate the mean of all of this. Okay. So does this kind of make sense, what we're attempting to do? Maybe. All right, well, this is what it looks like mathematically, okay? So here I'm going to just generate 1,000,000 values from the exponential distribution. I'm going to calculate the weight. The weight is found by doing the density for each value of x, and then we're going to divide by the density, exponential density for each value of x. All right, and those are the w's. All right, and so this is my estimate with importance sampling. Okay, and so that's 0.7976598. That's my thing. All right, here, this is what would happen is z comes from the normal, and then I'm taking the absolute value of z and I'm calculating the mean. And so this is another Monte Carlo estimate. And then here's the theoretic value. The theoretic is the square root of 2 over pi. This is if you did take if you did the analytic solution. So this is, found analytically. Okay, and so we can see all of these things are pretty close. We're at least accurate at least to 3 decimal places. They all start off with 0.797. So I got 0.7976, 0.79738, 0.79788. So in our case, our importance sampling estimate actually ends up closer than generating values from the normal distribution. I think that's just a coincidence. And if we were to repeat this several times, we'd probably get some kind of distribution where, some of these things are a little bit more likely, other things are a little bit less likely. But it seems like it's working okay. So so that's what we have here. Okay. All right, let me give you your second view quiz answer. And the second view quiz answer is the letter C. This kind of just illustrates how what the weights look like. All right, so this here, the blue, this is our normal PDF. And blue is the normal PDF, I think, times 2. So this is the PDF of the folded normal distribution. This is our exponential PDF. So this is 2e to the negative 2x. And then, and so here, the black line represents the relative weights. Okay, so these are the weights, which is, the weights are equal to f of x divided by g of x. And so locations around 0, the exponential produces too many values close to 0. So they get weighted less, okay? Whereas the exponential distribution doesn't produce enough values around 1.0, okay? Or 2.0, really, okay? So the exponential values doesn't produce enough, okay? So here it dips below between here, here and here, okay? It doesn't produce enough, and so those values are weighted more heavily, okay? When the exponential and the normal PDF are at the same location, they produce here values around 0.5 are produced the perfect amount from the exponential distribution, and they're as the folded normal PDF. And so those weights are exactly 1. Okay, values around 3.5 also produced at the exact right amount here. Okay, but values less than 0.5, exponential produces too many of them. Values between 0.5 and 3.5, the exponential distribution doesn't provide enough of them. So we have to compensate by adjusting our weights. And that's what this graphic illustrates here. Okay, and if you account for that, if you take in the different weights, you can get a pretty good Monte Carlo estimate of whatever quantity that you're looking for. Okay, I have another example where we could do importance sampling. Okay, so what if we wanted to estimate, what's the probability that a random normal value ends up over 4.5, right? So this is kind of like the very tail end of a normal distribution, right? So we know that 99.7%, almost all values in the normal distribution are between 3 and -3. And here we're asking, so, if we go 0 and here's 1 and here's 2 and here's 3, we're going to have very little beyond out here, okay? But if I say, all right, what about 4.5? And I say, what is the tail area beyond 4.5? That's what I'm asking here. Right. And we can answer this using the answer can be found using P norm. And we get something, 3.397 times 10 to the -6, a very, very small number. All right, so this is the theoretic quantity. Okay, using the CDF function. But let's say we wanted to estimate this. Let's say we want to estimate this using just plain old Monte Carlo integration. Okay, well, the way we could do it is we generate a whole bunch of random values, right? So Z is going to be many random values from the normal. Many random values from the normal distribution. And then basically our h of x is an indicator function of basically a z greater than 4.5, right? So we have an indicator function is z greater than 4.5, and we're going to get kind of true false values. And when I say, okay, well, how many times did it happen? Well, after generating 1 million values from the normal distribution, I got 2 values that were greater than 4.5. Okay. And I mean, I could, try this out myself. And I don't know, maybe I'd get something a little bit different. So I could say, let's do Z is going to be R norm 1 million. And then let me sort Z decreasing equals true. Whoops. All right, so in this case, I got 1, 2, 3, 4. 4 values. 4 out of 1 million values were greater than 4.5. No, I'm sorry, 5 values. 5 values were greater than 4.5, okay? So in our case, my estimate would be 5 out of 1 million, okay? If I do this again, and I do, let's just do like the first 20 values here. Okay, so here I have 1, 2, 3, 4, 5, 6 values that were greater than 1 million, or greater than 4.5 out of 1 million. Here's another random sample. Here I have 1, 2, 3 values. And so you can see, because it's like such a rare thing, my estimates kind of end up all over the place. In one case, I would estimate here I got 2 out of a million. Here I got 3 out of a million. Over here I got, I don't know, 5 out of a million or 6 out of a million, something like that. So, you know, my estimate here kind of bounces around a lot. And the true value should be 3.397 times 10 to the minus 6. So, you know, what can I do to try to estimate this quantity? All right. So classical Monte Carlo integration, like theoretically it works, but, you know, even after generating a million values, you know, my answers aren't going to be super precise, because it's going to be something like 3 or 4 or 5 or 6 out of a million. Okay. So what we can do instead is we can generate values from a distribution that is, you know, going to produce more values that are greater than 4.5. Okay. So yeah, we can improve our accuracy just by sampling even more values, and that would work. Okay. Or we can kind of improve our estimate by using importance sampling. So what we're going to do here is, so here I've got an exponential distribution. If I start at 0 here, but basically I can just kind of shift everything to the right. Okay, and if I shift everything to the right, like this, okay, and it starts at 4.5, now I've got an exponential distribution. Oops. I have an exponential distribution that's going to produce a lot of values that are greater than 4.5. Okay, so we can just shift everything to the right. I'm going to take my exponential distribution, and I'm just going to add a constant. I'm just going to add 4.5 to everything, and just shift everything down to the right. Okay, and you know, because of kind of the memoryless property of the exponential distribution, this thing and this down here, like if you were to just zoom in here, this is exactly just as proportional to it, right? So, you know, what is the PDF of this thing? Okay, what is the PDF of g of x? Well, it's going to be an exponential distribution just divided by a constant, right? So basically what we want is we have an exponential distribution, and we know that this thing has to integrate to 1, and it's going to go from 4.5 to infinity. So, you know, whatever it is, I can just start off with an exponential distribution, e to the negative x, and we know there has to be some kind of constant, so that when I integrate this thing, it's going to equal 1. Okay, so we're going to have e to the negative x divided by some kind of constant. The constant is going to be whatever the area is. Okay, so if I just kind of take e to the negative x, and I just kind of basically take this area, whatever that area is, I can just kind of do that. So I'm going to, so when I evaluate the integral, e to the negative x, the antiderivative of that is negative e to the negative x. I'm going to evaluate from 4.5 to infinity. Well, e to the negative x of infinity is 0, okay? And then if I plug in 4.5, I'm going to get e to the negative 4.5. So really, g of x just ends up being e to the negative x minus 4.5. All right. So this is the PDF. This is the PDF of g of x that starts at 4.5. Okay. And therefore, when we want to calculate the weights, so, you know, here's my normal PDF. Right. And again, you know, 0, 1, 2, 3, and then here's 4, and here's 5, and we're basically like trying to get everything beyond this tail over here. Right. So this is my f of x. F of x is the normal PDF, and we want to kind of do this, whatever this is, and we're going to divide by g of x. Okay. where g of x is, so this is my normal PDF up here on top, and g of x on the bottom is my exponential PDF. Okay, but you know, x is greater than or equal to 4.5. And here, the function that I'm trying to evaluate is just, is my random value greater than 4.5? Okay, is it greater than 4.5? That's what we want to know. So, you know, we want to get, you know, what's the expected value if expected value of f of h of x, okay? And this is basically, you know, what's the expected value of, you know, is x greater than 4.5? All right, and so this is going to be basically my indicator function, x greater than 4.5 times f of x, okay, where f of x is normal PDF. No trouble writing here. But again, we can't generate from f, so we're going to generate from g. So what we're going to do is we're going to just generate random values from the exponential distribution, and then I'm going to add 4.5, right? And that resulting distribution is exactly equal to the exponential distribution that begins at 4.5, okay? And that works because of kind of the memoryless property of the exponential distribution, that you know, once you kind of condition that x is greater than some constant, you know, the probability of generating a value, you know, the you know, constant plus x is the same thing as just generating 0 plus x for any kind of thing in the exponential distribution, right? Exponential distribution is memoryless. So, and in our case, if all of my x values are going to be greater than 4.5, then h of x is going to equal 1 for all of my generated values. So this is what it's going to look like. I'm going to generate 1 million values from an exponential distribution, and I'm going to add 4.5. I'm going to add 4.5 to all of these values here. The weight that I have to figure out, f of x divided by g of x, I'm going to take the normal PDF, which is f of x, and I'm going to divide by my exponential PDF, which is x minus 4.5, you know, e to the, you know, x minus 4.5. That's my exponential PDF. So I'm going to do d exponential. My indicator function I is x greater than or equal to 4.5. Well, we know that's going to be 1 for all of my values x. And so my mean here is going to be, you know, the mean of h times w. I mean, it's kind of silly doing 1 times w here. But this is going to be my estimated value is I'm going to take the mean of h times w for each of the values that I've generated, okay? And my estimate is 3.39082. And that's pretty close to the theoretic actual value of 3.3976, you know. So we're getting a, you know, a much more precise answer than if we were to just generate values from the normal distribution directly and say, how many times did my normal distribution produce a value greater than 4.5? Okay. If you produce 1 million values, you might get 3 or 4 or 5 values out of 1 million that were greater than 4.5. But that's not enough to give you a pretty accurate estimate. You'd have to generate maybe 10 million or 100 million to try to get something, you know, remotely accurate to what we have. But here I generated 1 million values from the exponential distribution instead. And then I'm getting a, you know, a much more precise answer over here. Okay. That's it for today. Question 3. The answer is E. E is our third view quiz answer for today. And that will be it for our topic on importance sampling. All right, we'll go ahead and end here for today. Have a great rest of your day, and we'll see you next week.